Good morning, Professor Emmanuel in the Switzerland.
Yes, hello everybody.
Hello, nice to meet you again. Dr. Rifai cannot guide this talk due to an important reason. So I will be a moderator in this talk. Therefore, I would like to introduce myself. My name is Taufik. I am a leader in the Proton Accelerator Technology Research Group in Research Center for Accelerator Technology. I would like to welcome to Dr. Rohadi as a chairman of Research Organization for Nuclear Energy, and then welcome to Professor Emmanuel Tsesmelis as a speaker in this Accelerator Talk, and welcome to the audience. And thank you for attend this Accelerator Talk. This Accelerator Talk is our routine agenda. So this is the third talk about the Accelerator technology and Accelerator application. So welcome to this Accelerator Talk, third Accelerator Talk. In this talk, we will hear some presentation from Dr. Emmanuel Tsesmelis. But before we hear his talk, so I would like to ask Dr. Rohadi Awaludin as chairman of Research Organization for Nuclear Energy to give opening remarks. Therefore, I would like to ask Dr. Rohadi. Time is yours.
Thank you, Pak Taufik. Can you hear my voice?
Yes, we can hear.
Okay, good. Thank you. Good evening, ladies and gentlemen, Indonesia, and good morning, our distinguished speaker, Professor Emmanuel Tsesmelis from European Organization for Nuclear Research. Thank you very much, Professor Emmanuel Tsesmelis, for joining us today. I believe that your talk will be very useful for us here in Indonesia. And ladies and gentlemen, all participants, first of all, I would like to welcome your participant in our session today. It is the third Accelerator Talk. Today, the talk will be about Cern Facility and Education Program. It will be delivered by Professor Emmanuel Tsesmelis. He will give us lecture about Cern facility, programs, and the research institution. Ladies and gentlemen, as we all know that recently, accelerator technology is developing rapidly. And here in Indonesia, we have Research Center for Accelerator Technology and Research Organization for Nuclear Energy. Hopefully, that this research center, can accelerate the development of accelerator technology and also human resources in accelerator in Indonesia. Ladies and gentlemen, lastly, I would like to thank all committee members of the session and the member of the Research Center for holding this Accelerator Talk. I do really hope that this session can be continued more frequently. And my special thanks goes to our speakers today, Professor Emmanuel Tsesmelis, who are willing to share your knowledge, information, and experience with us today. And we are looking forward to enjoying your lecture. And all participants, please enjoy the presentation and discussion. Thank you very much.
Thank you very much for Dr. Rohadi for your opening remarks. Now we will enter to the talk about the accelerator technology, Cern facility and educational program. But before that, I would like to read his curriculum vitae from Professor Emmanuel Tsesmelis. Professor Emmanuel Tsesmelis is a senior physicist and deputy head of international relations in Cern Director General Unit. And he is also visiting professor in particle and accelerator physics at the University of Oxford. And his education is PhD in experimental particle physics at the University of Dortmund. And his research is the discovery of Higgs boson and Cern neutrino program. So that's his profile. And now I would like to ask to Professor Emmanuel to give a talk, but in this talk we will have 30 minutes for speaker, and then we have 30 minutes for ask and answer the question. Okay, I would like to ask to Professor Emmanuel to give a speaker.
Thank you.
Please.
Thank you so much for the very welcoming introduction, and for the very welcoming hospitality, even though it is via Zoom, and very much my appreciation to BRIN for organizing these webinars. And I'm very happy to convey today some information from Europe, both from Cern and also from the University of Oxford, which I'm a visiting professor at. So let me just share my slide, and hopefully this you can see. Hopefully my slides. Okay, and I'll go into full mode. Yeah. So okay. So this is what there is some background information in this presentation on Cern itself, and also because I am very much working together with the John Adams Institute at the University of Oxford and in London, in Oxford and other universities in London. I will bring across some of the opportunities for student study possibilities in accelerator science and technology in this presentation. So the first part of my talk will focus on Cern itself, and I don't know, maybe some of you have visited Cern in the past, but Cern has become the biggest laboratory for particle physics research in the world, and this shows the facility, the Large Hadron Collider, the 27-kilometer ring tunnel in which the synchrotron is housed. And you can see here the airport of Geneva and the Lake of Geneva and the city of Geneva in comparison to this research infrastructure called the Large Hadron Collider, the LHC. A very interesting feature of this facility is that given its size and its location, it does straddle the border between France and Switzerland, and there's the border just there, cutting right across the LHC itself. The goal of Cern and of the LHC in particular is to understand the most fundamental particles and the laws of the universe, and this is done via the collider environment that we have built around the Large Hadron Collider. So Cern's mission, and I think this is particularly relevant to today's discussion, the core part of its mission is scientific research in particle physics. However, in order to do that, we need to develop the technologies at the forefront of individual fields, and in particular in accelerator science and technology. And that very much comes along to the discussion later today. This is very much supported by many programs in education and training, in particle physics, but also in the accelerator science and applied science and engineering, which are required to do this experimental particle physics research. And all this happens within the environment of the international collaboration. So if you look at each one of these in turn, each one of these four pillars of Cern's mission, the core part of the mission is scientific research in particle physics. And this shows you an image of one of the large experiments at the Large Hadron Collider, the ATLAS experiment, a little bit before being completed in its construction phase. And you can see here the size and the complexity of these large detector systems, which have been built through a collaboration of more than 3,000 physicists and engineers and technicians working to put this apparatus together. So the goal, the scientific goal, is actually to do two main aspects. One is to understand the nature of matter and what are the elementary building blocks of matter and the forces that control their behavior and the interaction between matter. So from an everyday environment of about a meter, the world around us, we know in the past 100 years we've been able to probe the finer structure of this matter down to the level of the quarks, which are 10 to the minus 18 meters in diameter. So those are today the most fundamental elementary building blocks of matter. And we study both the quarks themselves, but also perhaps substructure of the quarks, which may become visible to higher energy collisions in the LHC and other machines that we have here at Cern. So this is the crowning achievement, one of the crowning achievements, I would say, in particle physics over the past century, from the discovery of the electron at the end of the 19th century to where we are today with quarks and other fundamental particles, which have been explored and discovered at accelerator facilities, just like the Large Hadron Collider. Another way to look at things is in terms of time, and to reproduce the history of the universe from the time of the Big Bang, of the so-called time zero, to where we are today, 13.8 billion years later. So together with our colleagues in astronomy using telescopes, and we actually probe the very beginnings, a fraction of a second after the universe, after the Big Bang itself, using techniques based around accelerators. And like the Large Hadron Collider, allows us to reproduce the conditions of matter and energy at the very beginning of the universe's history, about 13.8 billion years ago. So those are the two main aspects of doing research in fundamental particle physics, is to understand the composition of matter and also understand what happened or what was happening at that very beginning of the universe, just a fraction of a second after the Big Bang. And what are the technologies that we need to do this fundamental research? Of course, at the core are accelerators, and this shows you the LHC, in the tunnel, this 27 kilometer circumference ring I showed you earlier. The actual synchrotron is situated in the tunnel, 100 meters underground, in the Geneva area. And here what you see is a series of dipole magnets which actually steer the beams around the circular trajectory of the 27 kilometers. We bring those beams of record energies and record speeds and record intensities to collision, where we have brought together 4 very large detectors. This is the CMS experiment. You saw the ATLAS experiment earlier, and this is the CMS experiment, where in the center of these detectors, the 2 counter-rotating beams in the synchrotron come into collision, and that energy of collision can produce new particles which existed at the beginnings of the universe. And of course, the third element in this research, which is needed, the third technology is big data computing. As we see, we have a lot of data coming out of the LHC, which is required to, and we need the computing infrastructure to store and analyze this data. So if we look at the accelerator in Cern, again, this is the photo of the LHC tunnel and the synchrotron, 27 kilometer circumference ring, 100 meters underground. And the key technology here and the enabling technology is superconductivity, which is applied to the construction of superconducting magnets to steer the beams around the ring in the 27-kilometer ring. And here you see the two beam pipes, which are continuous around the ring inside these dipole magnets. Each one of these magnets is about 15 meters in length and weighs 35 tons. And if you look closely, you can see the two counter-circulating beams of protons accelerated close to the speed of light at record energies, which today has reached 6.8 TeV in each beam. And the superconductor in this particular case is niobium titanium, and this is sitting in a superfluid helium bath at 1.9 Kelvin, which is about minus 271 Celsius. So it's the largest superconducting machine ever built, and the enabling technology, as I said, is the superconductivity and the whole cryogenic infrastructure, which is required to cool this machine down to 1.9 Kelvin. So around the ring, around the 27-kilometer ring, these beams cross and come into collision at 4 locations, and those 4 locations around which we have built these large detectors: ATLAS, CMS, ALICE, and LHCb, which record the products of these collisions for subsequent offline analysis and research for new particle physics phenomena and particles. And these, each one of these detectors themselves is built up by very large scientific collaborations built from scientists, engineers, technicians, and students having worked in the design, construction, commissioning, and today operation of this facility. So the worldwide computing grid is the scientific computing infrastructure which is required to store, distribute, process, and analyze the large volume of data which comes out of the LHC every year. We need about 1 million processing cores, which is distributed in about 170 data centers around the world in about 42 countries, pulling together about more than 1,000 petabytes of Cern data, which is stored worldwide in these data centers. 1,000 petabytes is 1 exabyte of data currently stored in this grid infrastructure. In addition to the LHC, we have built up over the years many other accelerators which provide a physics program or science program in nuclear physics, in the research of antimatter, in the study of climate change, in aspects like cosmic rays, between the connection between cosmic rays and cloud formation. And we have other fixed target experiments for searches of rare phenomena. And these lower energy machines have serve 2 purposes. One, they serve the purpose of injectors into the LHC, part of the injector chain to the LHC, but they also have their own science programs, individual science programs on those accelerators themselves. So it's a very diverse program of science. The flagship program is the LHC, but very diverse and rich program on the other accelerators. The first one, which is still in operation today, was built in the 1950s and still provides beams to the LHC and also to the solder facility and also to the cloud facility experiments and to the fixed target experiments at the Proton synchrotron. So we are in the process now of upgrading the LHC to what it's called the High Luminosity Lhc, is currently underway in order to provide, with the new technologies, 10 times more collisions than currently the LHC provides, and providing access to rare phenomena, greater precision, and discovery potential of what the LHC can do. We hope to start operating the high luminosity version of the LHC towards the end of this decade, and it will run until about the early 2040s. And beyond that, the roadmap for the European strategy of particle physics was updated a couple of years ago. And of course, the LHC and the high luminosity LHC feature highly in that roadmap for physics in Europe. But we also started looking beyond the LHC program to a new research infrastructure, which is based around the Future Circular Collider, the FCC. And you can see that in comparison to the LHC, it's a much larger machine, about between 90 and 100 kilometers in circumference, as you can see there. And initially, it will serve as an electron-positron collider to really study the properties of the Higgs boson and other electroweak physics, and then upgraded to a proton-proton collider in this same tunnel. And that will take physics research at accelerators at Cern towards the end of this century. So international collaboration. CERN was founded in 1954 by 12 European member states. Today, we have grown to 23 member states. Not all are European. We've opened the doors to countries beyond Europe's borders, and we also have 10 associate member states and also observers, 6 observers. We also have bilateral agreements with the governments of more than 50 countries and CERN, 15 non-member states and territories. We hope, and this is one of the aims, I hope in the coming months, to actually conclude an international cooperation agreement also with Indonesia, and that will be and that will cement and provide a framework for the collaboration between Indonesia and CERN. We have a staff of about 2,600 and about 800 postdoctoral fellows, and very importantly, we have more than 11,000 scientific associates working as users on one of our facilities, whether it's the LHC or other facilities. And if you see where all these users come from, this is a snapshot at the end of last year where the home institutes are located. You can see many of them come from the member states and the associate member states and observers, but we have a sizable community coming from the non-member states and territories. And on that particular day, we had 6 scientists registered at CERN to carry out the scientific research on one of our facilities. So it's very much a very impressive geographical and cultural diversity, which is illustrated by this by these figures. We have users of 110 different nationalities, of which 20% are female. So this is really one of the reasons why CERN has become such a very large center for particle physics research, given these numbers. So moving along to technology and innovation, the technologies developed for the accelerators and the detectors for the LHC and for the high luminosity LHC and can find applications in many other fields. Back more than 30 years ago, CERN was the birthplace of the World Wide Web, which has revolutionized the way we live and work. But there are many other examples of applying technologies developed for accelerators and detectors and computing in the area of medical imaging, cancer therapy, material science, cultural heritage, aerospace, automotive, environment, health and safety, industrial processes, etc. I will just mention the innovations in technology as applied to medicine and healthcare. The accelerated technologies developed for the LHC have found applications for cancer therapy with the use of protons, ions, and electrons. And CERN has been instrumental in transferring that know-how and technology across into this cancer therapy field. We have also been instrumental in conveying the technologies applied at CERN for the detectors, the sensors and the electronics into the next generation of positron emission tomographs, PET devices for medical imaging and diagnostics. The latest pixel detect technologies used in Atlas and CMS, for example, have found the use in developing a frontier high-resolution 3D color X-ray image This is the first image of the human wrist, which is very different than a black and white X-ray image that you have in a conventional facility. So this shows much more information and much more detail of the image under study. And at a facility called Medicis, at the Solder infrastructure, we produce innovative radioisotopes for research in nuclear medicine for the next generation of imaging devices, for example. So these are all applications of the technologies coming from Cern. Education and training, a very important picture is the age distribution of scientists working at Cern, a very wide distribution of ages, with very importantly, the peak being in the mid-20s. And this peak represents the more than 3,000 graduate students that we have at Cern working on one of our experiments, and predominantly on one of the LHC experiments. And very importantly, when they do graduate, not about 10 to 15% continue in careers in particle physics. About half of the graduating students obtain first employment in industry. About 40% go into academia or other research areas at universities or government labs, and about 20% move into other fields such as finance or government organizations. So this is very important because the training students obtain working at Cern can not only be applied to particle physics research, but can find applications well beyond that domain of fundamental science. We have many programs at Cern. We've had, as I'll say in a minute, we've had many, in the past years, we've had students, undergraduate students coming from Indonesia, joining the more than 300 undergraduate students in the Cern non-member state summer student program. We have more than 3,000 registered PhD students from a host university outside of Cern working at Cern. We have more than 1,000 fellows, technical and doctoral students in research and applied physics, engineering, and computing. We've trained more than 13,000 secondary school teachers. We have more than 150,000 visitors and guided tours. We engage with countries through traveling exhibitions, and we will have a new science gateway open next year here at Cern for the public engagement in science. So this is all part of the effort of training, education, and outreach at Cern that we offer to various countries. So I'll just spend a minute talking about the Cern non-member state summer student program, of which we've had undergraduate students participating from Indonesia over many years. And this is a beautiful program for advanced undergraduate students in the 3rd or 4th years of studies. And it's really a wonderful program of consisting of lectures in physics and engineering and IT. There's an internship program, a project for the students to work on with one of the research teams. There are visits, there are a web fest, there's a hackathon, there's workshops, and there's a culture exchange amongst the close to 100 different nationalities of students working in this program, under this program. So this is, I encourage many applications from Indonesian students to come on one of these programs in the future. And it is really a fascinating event to participate in for young students. This is the cohort of students in 2019, just before COVID broke out. You can see where they come from. Really, it's very close to 100 different nationalities. And we did have, as I said, one student from Indonesia participating in the program in that particular year, as is indicated in this map of the world. So we will be opening up the call for applications for next year's program in 2023 towards the end of this year. So please visit the Cern website and apply if you're eligible. There are certain eligibility criteria. which are required in terms of your stage of studies and letters of recommendation, and whether you are enrolled at a university at that time. So we look forward to receive many applications from Indonesian students later this year for next year's program, which runs in July and August for 8 weeks every year. So we also have a new program, which is called the Cern Non-Member State Doctoral Studentships. And this is in any area in particle physics, accelerated science, applied physics, computer science, and related disciplines. And this is really to build capacity in the country particularly for communities which are in development. And we hope to start this scheme. It's already in the pilot scheme, and we will be extending this program next year, depending on the external funding that we will have. So this is basically consists of students have started or about to start a PhD program in one of the above areas, and they will be spending up to 2 years at Cern, and the remaining of the time back in their home university. In this particular case, in Indonesia, and the academic arrangements are agreed between the university thesis supervisor and the Cern supervisor, thus setting up a partnership between the home university and Cern to cover the full duration of the PhD studies of the student. So again, I encourage you, if we do have a position, which will depend on the level of external funding, through the individual country funding agency or through the Cern and Society Foundation, we will open up a call for positions for nationals from Indonesia. And I hope we can do that in agreement with the authorities in Indonesia sometime next year to launch this program for Indonesian students. Now, as I said earlier, we do collaborate with more than 800 different universities from around the world. The one I'm particularly involved in is the John Adams Institute for Accelerator Science, which consists of 3 universities: the University of Oxford, the Imperial College London, and Royal Holloway University of London. And the John Adams Institute is a UK Centre of Excellence for advanced and novel accelerator technology, which provides expertise, research, development, and training in accelerator science and technologies, and promotes the advanced accelerator applications for science and also for society. It was set up close to 20 years ago and is comprised of groups from these 3 universities in the UK. We are 20 professors, 29 staff, and very close to 40 DPhil students in one of the accelerated science and technology domains of interest. The research projects are carried out at Cern, at DAISY in Hamburg in Germany, KK in Japan, Daresbury, Diamond, ICES, and the Central Asia facility in the UK. And we also have, in addition to research, there is a comprehensive training program consisting of obligatory lecture program in accelerated science and technologies. So these are some of the research activities which are carried out in one of these laboratories I mentioned earlier. I'll leave this in for the slides, but we do have interests and contributions to electron accelerators, proton accelerators, advanced acceleration techniques, novel instrumentation for particle beams, and also particle beam therapy using electrons and protons. So it's, as you can see, it's a very wide and broad areas of a research program carried out by the academic staff, faculty, and also by the students, the DPhil students, which are carrying out research for their PhD thesis. And to finish off, we have as I said, we have a very detailed program of lectures covering many aspects of accelerated science and technology. As you can see here, the list of lectures, and also this is supplemented by tutorials and exercise classes, which bring home the details of coming out of these lectures. So this is offered over 2 terms, October to December. This is the program from last academic year. And then this is followed by more detailed lectures, more specialized lectures in areas of accelerated science and technology in term 2. And again, this is over 8 weeks. And very importantly, there is a project, a student design project, which the students do over the 8 weeks, bring together as a team what they've learned in the lectures and exercise classes into designing a new accelerator. It could be, for example, this year, it was the Future Circular Collider electron-positron machine. Aspects of that facility were studied and designed by the student body. So that brings me to the end of the presentation. And I'd like to thank you for your interest. And I hope that this will allow exploration of possibilities of a collaboration between Indonesia and Cern and the John Adams Institute in education and training for PhD students. Thank you very much.
You're welcome. Thank you very much for Professor Emmanuel for your nice presentation. So I think that's a really interesting presentation. You have talked about the Accelerator research project in the Cern and some of the collaboration and also education for the student. So I hope there are many questions about this for study in Cern and in about the accelerator technology. Okay,
yes.
Now it's time to enter to the discussion time. So if the audience have a question, you can raise hand or write in the chat room. So please, if you have a question. Is there any question? Before some audience give a question, I would like to ask you about the doctoral student. If someone want to apply to the Cern doctoral student, is there any basic knowledge that should the student candidate have? Is there any basic, such a accelerator, basic accelerator or something? Is there any basic knowledge?
Yeah, I think the doctoral student program, if you are looking to do a PhD in accelerator science, typically you would have done an undergraduate degree in physics, not necessarily accelerator physics, but it could be in particle physics or it could be in an engineering field. Electrical engineering is a good candidate. Those are the 2 key areas where students have studied at an undergraduate level and then become trained at Cern for a degree in accelerator physics. But the basis would be an undergraduate degree in physics or engineering. Yeah, otherwise it becomes quite difficult to follow. There would be support, but at the John Adams Institute, for example, the first 2 terms of the first year are dedicated to coursework and a design project. So students who come from different fields in physics and engineering get the basic training to become at the same level of knowledge in accelerator science, in accelerator physics. At Cern, we don't offer courses as such, but we do run the so-called Cern Accelerator School, which, and there are many, and it's called the CAS School, which runs on an annual basis. And that offers, it's very much a compact school of a couple of weeks where the students get the basis of accelerated physics in case they don't come from a relevant field of physics or engineering as undergraduates. So that one I would also recommend is the Cern Accelerator School.
Okay, thank you very much. There is a question from Mr. Silahuddin.
Yeah.
Is there in Cern any program collaboration to? I mean, is there in Cern any program collaboration to develop cyclotron for medical use?
Yeah, we do have a group here which is developing accelerators for medical applications, both at Cern and also at the John Adams Institute. And if that's the way you want, the student would like to do research on that, we can certainly discuss a possibility with the professor, which will be the supervisor. We do carry out those that research at Cern and at John Adams Institute.
Okay, but in cyclotron research, is there a new cyclotron type, or just application of the cyclotron?
Yeah, so at the moment we're looking more at applications of cyclotrons. Now there is a group at PSI in Switzerland, which is doing research in new generation cyclotrons. But having said that, we do in the John Adams Institute training, we do have lectures on cyclotrons. And perhaps the student can do a PhD with a professor who's a professor from PSI in cyclotrons, in developing new generation cyclotrons. Yeah.
Okay, thank you. Yes. Okay, there is one question again from Dr. Emi Mulyani. Is it possible if, for example, we take a PhD degree in university in Indonesia, but then we join a group in Cern and do an experiment? Is there?
Yeah. So these the doctoral studentships I mentioned earlier from Cern, they have to be done in conjunction, with the university in Indonesia and Cern. So the student will spend up to 2 years at Cern, and the remainder of the period to do the PhD will be back at the home university in Indonesia. And the research project and the supervision will be done jointly between the supervisor in Indonesia and one at Cern. So that is it's a joint effort between Cern and Indonesian Institute. Yeah, but there will be you'll be spending time both at Cern and also in Indonesia. For the John Adams program, John Adams Institute, there you will be based full-time in Europe, well, at the John Adams Institute, but of course, depending where your research is, if that is at Cern, then you'll spend substantial amount of time seconded out to Cern, or it could be at DAISY, or it could be at KEK. It depends on the project.
Okay, thank you. There is one question again from Mr. Imam Kambali. So first question is: Do you also use laser assist particle acceleration at LHC? And what kind of accelerator technology currently developed by Cern to reach the experimental goal from the years of 2029 to 2040?
Right. So for the first question, we don't have laser assisted acceleration at Cern at the LHC, but we do have a dedicated research project which is called AWAKE, and that's not laser, but it's actually proton driven plasma acceleration. So this is one of the advanced acceleration techniques which I referred to earlier, where you create a wake field firing a high energy beam of protons into a plasma, and that wake field provides the accelerating electric field. And that experiment is based at Cern. We do have students from Oxford actually, which are participating in that program, and they will get their degrees from the University of Oxford. But the research facility called AWAKE is at the Cern SPS machine accelerator. Yeah. For the second question, the enabling technology there is to develop higher field magnets based on new types of superconductor. The LHC magnets, the superconductor there, the dipole magnets, they're based on niobium titanium alloy. What we're looking at now is to build high, and they operate at 8.5 Tesla. We want to build next generation magnets to operate at 11.5 Tesla, which will be we would require another type of superconductor like niobium tin, and that is under development for this for these machines, for the high luminosity LHC, and that will operate up to 11.5 Tesla. And then we also have to develop these magnets using maybe niobium 3 tin or perhaps high temperature superconductor for the future circular collider hadron-hadron machine, which will probably require magnets going up to 16 Tesla or perhaps 17 Tesla, depending on what the final circumference of the ring is. So this is a lot of effort is going into superconducting magnets and also superconducting radio frequency cavities, because for the electron-positron collider of the FCC, there we would require operation of a superconducting RF at various different frequencies, 400, 800 megahertz, to be able to accelerate the particles of electrons and positrons in the FCC EE machine.
Okay, thank you for your answer. There is another question. Is there any collaboration plan between Indonesia or BRIN and Cern regarding the human research capacity building in accelerator field?
Yeah, so I think the fact that we have initiated now a discussion between BRIN and Cern, we hopefully will be able to sign international cooperation agreement, which I would very much like that, and that will provide the framework for strengthening our collaboration, and we could certainly move towards areas of accelerator science and technology. At the moment, we have no current cooperation in that area, but I believe that we could explore ways to do that through an international cooperation agreement.
Thank you. Is there any question from the audience? You can raise hand. This one question. What kind of control system is used at CERN? Is there any program for electrical instruments students to do research at CERN?
Yeah, certainly the control system is very much based on, there's a whole team based on beam instrumentation. And so this beam instrumentation group, first of all, builds the sensors in the accelerator. And then there's another group called the controls group, which actually provides the control system for the accelerator. But obviously, you can imagine that these two groups have to work very close together. So if one chooses, one can work to do a PhD in control systems for the accelerator of the LHC, also for the future machines. And this is, I don't know the exact technology which is used, but there's always a need for young people to carry out research in that area, whether it's on the sensors or on the beam instrumentation and diagnostics, which is based on sensors and electronics, or on the controls group itself, which controls the machine. Yeah. So the other question I see is the high luminosity LHC. So the LHC itself is designed to operate at 7 TeV beam energies, proton beam energy. We have reached today 6.8 TeV. So we will, at the next stage, we will go hopefully up to 7 TeV in the next phase of operation. The next phase will also include the high luminosity LHC, which is effectively an increase in the collision rate expressed by luminosity. So, and that will be operating, there we need much more powerful quadrupole magnets very close to the interaction region of the experiments, Atlas and CMS, where the beam sizes will be smaller than what they are today at the LHC. And that's where we need powerful magnets to actually squeeze the beams down to smaller transverse dimensions and increase the probability of collision as these two beams of clouds of beams cross each other at the center of the experiments. And that is the main aim to do that, high luminosity Lhc, in order to have more statistics to study the Higgs boson and perhaps identify physics beyond the standard model of particle physics, with hopefully the discovery of particles making up the so-called dark matter that we observe indirectly in the universe.
Okay.
How much money will be invested in the high luminosity project? It's about $1 billion, which is the overall cost.
Oh, shit. That's very good. Okay, thank you. Next question is from Maggie Stefanus. There are two questions. Is there any opportunity to conduct research photon X-ray tomography at Cern? Could you please?
Yes. So we do. We're not a synchrotron light source, but then I would like to refer you to the John Adams Institute, where we do work very closely with the Diamond Light Source, which is the national UK synchrotron light source facility with X-ray beams. And if you would like to do a PhD in that area, it's now a good moment because the Diamond facility is in the process of being upgraded to higher brilliance. So that would be...
The location is at Cern or no?
No, this will be... Diamond is in the UK, very close to Oxford.
I see.
Yeah.
Okay.
So, but the John Adams Institute has a group working in that area. Yeah.
Okay. And then second question, could you please specifically mention the division laboratory or group which provide this? I think you have.
Yeah, that's the John Adams Institute.
Okay, I see. Thank you very much. Is there any question from the audience? So usually my friend is from mechanical engineering. I would want to apply to the Cern or Accelerator technology, but should they study about physical accelerator physics in detail or just introduction?
If they can certainly do a doctoral program at Cern on a project which is mechanical engineering. Okay, so for example, the vacuum group, colleagues of mine working in the vacuum group have all had undergraduate studies and PhD in mechanical engineering. So mechanical engineering and electrical engineering, there are many projects which they don't have to necessarily come with knowledge of accelerator physics, but they should obtain that knowledge during the course of their PhD studies and by attending different schools and lectures which are offered at Cern and so forth. But mechanical engineers and electrical engineers, you will find them in many groups here at Cern on building much of the infrastructure that we require for accelerators.
Okay, thank you very much.
But they should have, as I said earlier, the basis should be some area of physics and or engineering.
Okay, I see. Okay, one question again from Mr. Bayu Mahdi. How long does it take for doctoral student program in Cern, especially for accelerator science research? Thank you.
So this depends, actually, because Cern does not provide the degrees, this depends on your university in Indonesia. So if a PhD takes 3 years, or if it takes 4 years in Indonesia, that's how long it takes. We would provide the possibility for the student to come to Cern for up to 2 years of that period. So I presume in Indonesia it probably takes 4 years to complete a PhD.
3 years, 3 years. Maybe.
3 years.
Yes.
So 2 of those 3 years can be spent at CERN, maybe not in one go. Maybe the students come for 1 year, go back for 6 months, come back for another year, and then go back to Indonesia to complete and write up the thesis.
So if we want to apply research in CERN, should we apply to CERN website or just open the John Adam website, right, and then we apply to the John Adam?
Yeah. So for the there are 2 different ways. The CERN program is only open to non-member state nationals once we have confirmed funding, external funding. Now, for Indonesian students, we don't have today any funding, but this is something hopefully we can discuss with BRIN to see if there are possibilities there. For John Adams as well, there would be a call for applications on the Department of Physics website of University of Oxford, or of the other 2 universities, Imperial College London and Royal Holloway, University of London. So there you have to follow the standard procedure for applying to the Department of Physics to do a PhD. And then your application, since you specify John Adams Institute, will be directed to the professors of the institute. Again, this very much depends on external funding from Indonesia, because the UK national funding is only for British nationals to fund.
Okay.
So we can find other funding from third parties to support the students. So there, this is something we will probably discuss with BRIN, maybe in a separate meeting, how to arrange for funding for students to be trained either at CERN through the CERN doctoral student program, or at the John Adams Institute.
Okay, maybe we can discuss more later about the cooperation.
Yes.
Is there any question from others? We only have 3 minutes again. If no, maybe we can stop this talk, and I would like to thank to Professor Emmanuel for your presentation, So there are many Indonesian candidate students who are very interesting to study in CERN. As you know, in Indonesian, Accelerator facilitator is not so much. So there are only several, 1 or 2 facility in research facility in Indonesia. So I think this is good for us to study in CERN, because of CERN is more advanced in accelerator technology. So I thank you very much for your presentation.
Okay. Thank you.
Yeah, I can.
And I hope we can continue this discussion to see how we can form a framework for collaboration, both with CERN and also with the John Adams Institute.
Yes, I hope so. I will ask to Dr. Rifai to maybe to make a more communication about this doctoral program.
Yeah.
Is the Dr. Rohadi, do you have any close statement?
Okay, thank you, Pak Taufik.
Yeah.
Thank you very much, Professor Tsesmelis, for your interesting and very useful lecture to us here in Indonesia. And hopefully, collaboration between BRIN and CERN will be more intensive in the near future. And I heard that our chairman of BRIN will visit also CERN in the near future, and hopefully we can more intensive collaboration, and we can send our young researchers to CERN to study about accelerator. Thank you very much for your time today.
Thank you so much also from my part. And we look very much forward to welcoming the chairman to CERN to show the facilities around and also discuss collaboration.
Yeah, okay, thank you very much.
Thank you.
Yeah, thank you, Dr.
Bye bye, everyone.
Okay, bye bye. Terima kasih Bapak-Bapak, mungkin sekian saja kita tutup untuk Accelerator Talk ini. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Pak.
Sama-sama Pak.